Struggling with math? You're in the right place. Welcome to Explaining Mathematics, the channel where we simplify tough problems, break down complex formulas, and turn confusion into clarity. From basics to advanced topics, we explain it all step by step. Let's start solving.
Let's talk about calculus. For a lot of people, that word sounds, well, intimidating. But what if I told you it's one of the most powerful and, honestly, beautiful ideas humans have ever come up with? Forget the complicated equations for a second. At its heart, calculus is simply the language the universe uses to describe change. It's the mathematics of motion, of growth, of, well, everything that doesn't just stand still. And it all starts with a very simple and very tricky question.
So, let me ask you this. Whatever you're doing right now, what is your exact speed at this very instant? I don't mean your average speed over the last 5 minutes. I mean your speed right now. Seems simple, but hold on. How do you measure speed? You have to cover some distance over some amount of time, right? But an instant has 0 time. It's gone as soon as it's here. So how in the world can you measure speed in 0 time? It sounds like a paradox, but cracking this little puzzle is the key to unlocking all of differential calculus.
And this difference is everything. Look, average speed, that's a piece of cake. You drive 100 kilometers in 2 hours, your average speed is 50 kilometers per hour. We all learned that, but that average hides everything interesting. Were you stuck in traffic? Were you speeding? It doesn't say. But that little needle on your car's speedometer, that tells you your instantaneous speed. It solves the mystery for you. The question is, how? What kind of math is happening inside that little device to solve the paradox?
Okay, to crack that mystery, we need to learn the language it's written in. We need to grab a couple of essential tools for our toolkit. So before we get to the big aha moment, let's make sure we've got the basics down.
The first tool, and it's the most important one, is the idea of a function. And really, all a function is a consistent rule. It's like a recipe. You put one thing in, and you get exactly one thing out. Every time. No surprises. So if our rule is, say, f of x equals 2x plus 3, it just means whatever number you give me, I'm going to double it and add 3. You give it a 4, bam! You get an 11. Give it a 10, you get 23. It's a predictable machine. And it's how we describe the relationship between things, like the relationship between time and distance.
Now, talking about these rules is one thing, but the real power comes when we can actually see them. By plotting the inputs on one axis, the x-axis, and the outputs on the other, the y-axis, we get a picture, a visual story of our function's behavior. And this is so important, because once we have a picture, we can start to talk about things like its steepness or its slope. And that idea of slope, that's taking us right back to our original problem about speed.
All right, we've got our tools, we understand functions and graphs. Now it's time for the breakthrough. This is the big, brilliant idea that finally lets us measure change in a single instant. The conceptual leap that makes all of this work is the idea of a limit. It's a super clever workaround for our zero-time problem. The idea is, instead of trying to land exactly on a single point in time, what if we just sneak up on it? What value are we getting closer and closer and closer to as we approach that instant? We might never actually get there, but if we get infinitely close, we can see exactly where we were heading. This idea is the bedrock of all of calculus.
So how does this help? Well, let's go back to that graph of our car's journey, that big swooping curve. We want to find its steepness at one single point. But how do you measure the steepness of a curve? Here's the magic trick. What if you just zoom in? I mean, really zoom in on that one tiny point. As you get closer and closer, something amazing happens. That beautiful curve, it starts to look less like a curve and more like a perfectly straight line.
And that straight line that we're seeing when we zoom in, that's called the tangent line. It's a line that just perfectly kisses the curve at that one single point, matching its direction and its steepness for just that one moment. And the beautiful thing about a straight line is, we know how to find its slope. And right there, that's the solution we've been looking for. The slope of that tangent line is the instantaneous rate of change. It's the speed at that instant.
So, this big idea, this incredible measurement, it has a name. It is the star of the show, the derivative. Simply put, the derivative is a new function we create whose only job is to tell us the slope of the tangent line, the instantaneous rate of change, at any point we want on our original curve. So that mystery from the beginning, what's your instantaneous speed? It's the derivative of your position with respect to time. We've got our answer.
And I absolutely love this way of thinking about it. The derivative is a universal speedometer. But it's not just for cars. It can be a speedometer for a company's profit, a speedometer for how quickly a patient's temperature is rising, a speedometer for how fast a city's population is growing. Literally, if any quantity is changing, the derivative can tell you exactly how fast it's changing at any given moment.
Let's make this totally concrete. Imagine we have the function f of x equals x squared. This gives us a nice, simple, U-shaped curve called a parabola. Now, through the rules of calculus, we can find its derivative, which is just f prime of x equals 2x. Okay, so what? Well, this simple little function, 2x, is now our slope-finding machine. You want to know the slope of our curve at the point where x equals 1? Just plug 1 into the derivative. 2 times 1 is 2. The slope is 2. What about where x equals 3? Plug it in. 2 times 3 is 6. The curve is getting steeper, and our derivative tells us exactly how steep instantly.
So this is a seriously cool mathematical tool. But is it just a neat trick, or does it actually show up in the real world? Well, let's take a look at how this one big idea basically powers our entire modern world. Honestly, the applications are pretty much endless. Physics is basically built on derivatives. Calculating the velocity and acceleration of a rocket blasting into orbit, that's all derivatives. In business, finding the exact point where profit will be at its absolute maximum, that's a derivative problem. Engineers use them to find the strongest, most efficient shape for a bridge. Biologists use them to model how fast a disease might spread. Any field that studies how things change relies on the derivative. Let's try a classic example. A farmer has 20 meters of fence and wants to make a rectangular pen with the biggest possible area. How big should the sides be? Okay, first we create a function for the area. Then, here comes the magic. We find the derivative of that function. Now, why would we do that? Well, think of a graph of the area. It's a curve that goes up to a peak, the maximum area, and then comes back down. What's the slope at the very top of that peak? It's perfectly flat. The slope is 0. And since our derivative is the slope, all we have to do is set our derivative to 0 and solve. The math tells us the ideal length for side x is 5.
And there you have it. The biggest possible area the farmer can make is a perfect 5 by 5 square. Calculus just gave us the perfect answer, no guesswork involved. Now, I know this is a simple example, but this exact same process, finding a maximum by setting the derivative to 0, is how companies optimize their supply chains and how scientists find the most efficient chemical reactions.
So the derivative is clearly a really useful tool for solving problems. But its importance goes so much deeper than that. Getting your head around this idea gives you a fundamentally new way of looking at everything around you. Think about it. Before calculus, math was fantastic at describing things that were static, things that stood still. It could describe the angles in a pyramid or the shape of a field perfectly. But our world isn't static, is it? It's a movie, not a photograph. Things are constantly in motion. Calculus was the invention of a language that could finally describe the movie. It let us do the math for a world in constant flux.
Okay, so let's wrap this all up. What are the big takeaways? First, calculus, at its heart, is the study of change. Second, the clever idea of the limit is what lets us zoom in on an infinitely small moment in time. Third, this leads us to the derivative, our amazing tool for measuring the exact rate of change at that moment. And finally, this one idea is the foundation for pretty much all of modern science and technology.
So the real point here isn't just to learn some new math, it's to gain a new framework for thinking. You now have the fundamental tool for measuring and understanding change. So the question I'll leave you with is, what part of your world do you want to analyze? That's all for this explainer. Thanks for joining us.
If this video helped you understand the topic better, don't forget to like, subscribe, and turn on notifications so you never miss a lesson. Comment below what topic you want explained next. Thank you for watching Explaining Mathematics. See you in the next problem.